Welcome to Module 4. Module 4 is going to be on the input parameters used or required for pavement ME design. As a reminder from Module 1 on the course schedule or roadmap, Module 4 represents or presents the input variables required to use the pavement ME design software. Module 4 defines and overviews the inputs in summary. Module 4 is going to be separated into 4 input categories, just like in accordance with using the software. These 4 input categories are consistent basically with the pavement ME software. These are design criteria and reliability, climate, traffic, and finally material and layer properties. Each input category will be discussed separately throughout the workshop. We're going to start with Module 4.1 on the MEPDG design criteria and reliability. Module 4.1 builds or expands from Module 3, or the material presented under Module 3, as well as Module 2. There are 4 learning outcomes for Module 4.1 on design criteria and reliability. The first is to determine the design threshold values. The second is to identify the performance indicators for each design strategy. The third is to describe the impact of the design threshold values on layer thickness. And finally, the fourth learning outcome is to describe the combined impact of the design threshold and reliability values on layer thickness. Chapter 7 in the MEPDG Manual of Practice overviews the selection or selecting the design criteria and reliability level. As mentioned in Module 3 that we just previously covered, 7.1 provides the recommended design performance criteria. Section 7.2 is on or focuses on reliability, and Section 7.3 focuses on design reliability for smoothness, at least the concept for smoothness, as well as the distress criteria. So Module 3 that we just covered, we presented Module 7.2 and 7.3, and now we'll look at Section 7.1 on the recommended design criteria, design and performance criteria. So we will move to opening the MEPDG Manual of Practice. And we will go to the Section 7, Selecting Design Criteria and Reliability. And this, Module 4.1, focuses on recommended design and performance criteria. Table 7.1 or 7-1 provides the suggested design criteria and threshold values recommended for use in judging the acceptability of a design criteria. These are specifically given by roadway type or classification for each of the different performance criteria and for the pavement type. And then that we just covered in Module 3, Section 7.2 is on reliability, and then Section 7.3, design reliability concept for smoothness, and then Table 7.2, which will be covered in this module, provides a suggested or recommended minimum levels of reliability for different functional classifications of the roadway itself. So with that, we will go back to the presentation and continue. So design criteria and reliability. This is a screenshot of the design criteria and reliability values. The limit or the threshold value are given in this column, basically in this column, and the reliability values are given in this column in the software. And we will open the software in just a minute. There's a column, or the column on the right, report visibility. This has to do with where the user can consider each one of these that are checked in determining the acceptability of a design. The user can simply unclick them or uncheck them, and then a specific design criteria, as an example, performance deformation in the asphalt only. And the design and the software would still calculate the permanent deformation in the asphalt only, but it would not be used in making a judgment on whether the design is acceptable or not. So now let's open the software, and we will demonstrate or show where these are. So this is the Payment ME software version 3, and we want to go down to the performance criteria. And this is for new flexible pavements. And for the performance criteria, we have the initial IRI, asphalt thermal cracking in feet per mile, asphalt bottom-up fatigue cracking in percent total lane area, asphalt top-down fatigue cracking percent total lane area, permanent deformation in the asphalt only, permanent deformation total of the pavement, and then the terminal IRI in inches per mile. This shows the limits for each one, and this is the reliability level selected by the user for each one. This is the report visibility column, and so if we didn't want to include the rutting of the asphalt in determining whether our design was acceptable, we would simply unclick or uncheck this column, and it would not use that variable or threshold value for determining acceptability. Okay, if we now go to, that was for flexible pavements, we could also look at jointed plain concrete pavement, and then look at the performance criteria. And for that, we have the initial IRI, we have the terminal IRI in inches per mile, we have the transverse cracking fatigue or total percent crack slabs, and then the mean joint faulting column, the reliability level, and then the report visibility. We could also then turn our attention to the continuously reinforced pavement structure, and the design criteria in this case is initial IRI, terminal IRI, and then the number of CRCP punch-outs on a per mile basis. Again, reliability level, and then report visibility. The last one we'll take a quick look at is going to be the semi-rigid pavements. So if we do the semi-rigid pavements, you can see many of these are identical to the flexible pavement. Initial IRI, AC thermal cracking, AC bottom-up fatigue cracking, AC top-down fatigue cracking, permanent deformation in the asphalt layer only, total permanent deformation, terminal IRI, and then in addition, we have the chemically stabilized layer fatigue cracking in terms of percent total lane area. We also have then asphalt total fatigue cracking bottom up plus reflective of the fatigue cracks in the chemically stabilized layer. And then we have the AC total transverse cracking, thermal cracking in the AC new, or reflective cracking in terms of joints, or shrinkage cracks in the semi-rigid layer. And then we also have the reliability levels and report visibility. The user should note that there are some of these variables, like AC thermal cracking and then AC bottom-up fatigue cracking, where these are 50% reliability and the user does not have the capability to change these values. And also in the fatigue cracking in the chemically stabilized layer, the user cannot change these. The reason for that being the case is the reliability level is defined by the total fatigue cracking bottom plus reflective and not chemically stabilized layer. And then the same is true for AC thermal cracking and bottom-up fatigue cracking. The reason for that is the bottom-up fatigue cracking plus reflective, and then the AC thermal cracking plus reflective, are basically determined at the surface. So during calibration, it's impossible or very unlikely that we can separate transverse cracks new from transverse cracks that are reflective shrinkage cracks in the chemically stabilized layer, or to clearly and accurately define the difference between new bottom-up fatigue cracks in the asphalt versus reflective bottom-up fatigue cracks from the chemically stabilized layer. And so the calibration is only based on what we can accurately see and measure at the surface without doing test pits. So that's the reason these reliability values the user cannot change, and the reliability value is determined based on what we can see and measure at the surface. So it's the fatigue cracks plus new fatigue cracks in the AC plus reflective fatigue cracks from the chemically stabilized layer, and a new AC thermal cracking plus reflective shrinkage cracks from a chemically stabilized layer. So with that, we will now go back to the presentation and then continue. The design criteria is based on two parameters. We have the distress threshold values, also referred to as performance criteria, design criteria, and or failure criteria. Remember from Module 3 when we talked about reliability, these are basically the same or have the same meaning in terms of judging the acceptability of the design. Also, the user should also remember that these distress threshold values should come from the agency's pavement management system, or how the agency operates and maintains its roadway facilities. The MEPDG threshold values, we basically showed those in the screenshots or when we open the software. And now we're just going to briefly go through each one as a reminder. So For flexible pavements, we have total rut depths, bottom of fatigue cracks, top down fatigue cracks, transverse cracks, and then IRI. The user might remember that there's also the initial IRI is on the same screen. The initial IRI is not used to judge the acceptability of a design, or it's not considered a distress threshold value. But it is important to know what the starting value of IRI is for each distress hole or for each pavement design strategy. So the initial IRI is included in the MEPDG design threshold values in the software itself. For semi-rigid pavements, we have, as a reminder, we have the same distress threshold values for flexible pavements, but then we also have an additional threshold value based on reflection cracking. Reflection cracking of fatigue cracks and reflection cracking of transverse cracks for semi-rigid pavement. So we still also have total rut depth, bottom up fatigue cracks, top down fatigue cracks, transverse cracks, and the final or terminal IRI. Also, what we did not show is the rut depth in the asphalt layer only. The reason for that, the manual of practice recommends that the total rut depth be used as the design criteria, because what we see and measure at the surface is the rut depth from all layers combined. The asphalt layers, any unbound aggregate base layer, as well as the subgrade. So those are calculated separately in the software, but the manual of practice suggests that only the rut depth that we can see and measure at the surface be used as the design criteria or the threshold value to determine acceptability of a design. The MEPDG threshold values now for jointed plain concrete pavement. There are three. Faulting, the transverse joints, mid-slab cracking or percent crack slabs of the JPCP, and then the terminal IRI itself. For rigid pavements, we have only two: the number of punch-outs per mile, and then the terminal IRI. The distress threshold values, kind of reviewing back in the Module 2 that we have previously delivered, is simply defined as the acceptability of the design is determined by comparing the predicted distresses and smoothness against the distress threshold values. So it's basically the condition of the pavement for which major rehabilitation is required. This should come from or be determined by the agency's pavement management system data, or how the agency operates and maintains, rehabilitates its pavement structure. So the design should always be consistent with how the roadway, the policy of rehabilitating the roadway of the agency. The design fails or is considered unacceptable if the predicted distress is greater than the threshold value, or the predicted smoothness is greater than the threshold value. Establishing design or distress threshold values, two items here. Distress threshold values should reflect the agency policies regarding payment condition at which major rehabilitation is required. We just mentioned that previously, but this is an important concept, or an important concept required by the software. So we're going to mention this a couple times through the entire workshop. It's also quantified from an agency's payment management or performance database for which major rehabilitation was defined for the payment. It can be based on a survivability or failure analysis. It can also be based on engineering judgment. But whether it's based on a survivability analysis or engineering judgment, it should be tied to how the agency operates, maintains, or its policies on rehabilitation of its roadway network. Okay, the distress threshold values, the MEPDG manual of practice, or values that are included in the MEPDG manual of practice. We're going to show each one. We'll start with flexible payments first. And this simply shows the functional classification of the roadway, interstates, principal arterials, secondary arterials, and local roadways. We then show the typical or default threshold values that are in the MEPDG manual of practice, and each of these refers to a different risk consequence. Remember how we defined risk in Module 3. So very high volume interstate freeways have a high risk consequence. So the distress threshold values are generally lower for the higher volume roadways, and that value then decreases to local roadways where the risk consequence is low. And so the design threshold value, or the threshold value, is much higher. So as the risk of an event, the occurrence and consequence increases, the distress threshold value typically decreases. This table is also in the MEPDG manual of practice for fatigue cracking of jointed plain concrete pavement. The same values in the previous slide for flexible pavements are now shown, but for fatigue cracking of jointed plain concrete pavement. And so this percent cracked slabs and the values going from interstate, higher volume roadways to lower volume local roadways. And again, these are all in default values that are included in the manual of practice. Now for CRCP. So we're on continuously reinforced concrete pavements. Again, slide shows exactly the same thing as on the previous slides. The threshold values, punch outs per mile, going from high volume interstates to low volume local routes. So as a reminder, design reliability. We covered this in Module 3, but reliability is defined as the probability that a pavement design will perform its intended function for a specific period of time in a defined environment. And that environment includes climate, traffic, foundation, and other site factors without failure. Failure is the condition of the pavement for which major rehabilitation is required. So the reliability values, these are values, default values, suggested default values in the MEPDG manual of practice, and they are basically pavement independent. So we have our functional classification of the roadways going from high volume interstates to low volume local roadways, our risk consequence going from high to low, and then the reliability on whether it's an urban roadway or a rural roadway. and these are the suggested default values in the manual of practice. Again, the higher reliability values are for the high volume interstate, and then the lower reliability values are for the lower volume local roadways. Remember, as the risk of an event, the occurrence and/or consequence increases, the reliability value typically increases. In other words, going from local routes to interstate freeways or roadways. So what is the impact now of the threshold criteria or threshold values and reliability on layer thickness? So we're going to show now a series of charts for different pavement types and for different distress types. We're going to start with the impact. We're going to start with the examples on the impact of reliability on layer thickness. So the y-axis in these is the predicted fatigue cracking, percent cracked slabs for jointed plain concrete pavement fatigue cracking with age. And there are four reliability levels shown here. The solid curve is 50%, or the mean, based on means, 50% reliability. The next one is 75% reliability. The one above that is 90% reliability, and the one above that is 99% reliability. So you can get a feel or idea what impact does reliability have on the layer thickness. And it's a significant impact going from 50% reliability of about, say, 4 inches, all the way up to a 99% reliability of almost 20 inches. So it has a huge impact. Obviously, this is just an example because one would not build a 20-inch jointed plain concrete pavement, and other design variables in terms of different layer types, layer features, so that the thickness of the jointed plain concrete pavement wouldn't be as 20 inches. Other design features would be looked at so that the pavement design strategy could be optimized. So this is, again, just an example to show the impact of reliability on layer thickness. The bottom graph now is for asphalt fatigue cracking in terms of total percent lane area. And the same thing is given in terms of different reliability. So we have the y-axis, predicted bottom-up fatigue cracking. X-axis is age or the design life, 20 years. And then 4 reliability levels. The lower solid black curve is 50%. The next one is 75% reliability. The next one is a 90% reliability. And the next one is a 99% reliability. So again, reliability has a huge impact, significant impact on the layer thickness of basically all pavement design strategies. At 50% reliability, we have about, maybe 5.5 inches. The 75% is about 8. The 90% is about 10. And the 99% is slightly over 14 inches. Again, these are just examples for the impact on only the bound layer thickness. Obviously, other design parameters would be changed so that we do not have to build such thick bound layers to meet our design criteria. So now let's move to showing the same thing, the sensitivity of layer thickness, but to the distress threshold values. So this is JPCP on asphalt or embankment soil directly. In other words, there's no aggregate base. The pavement ME design optimization tool was used to create these bore charts, and the layer thickness was derived to the nearest 0.5 inches. Again, these are simply examples to show the impact of the distress threshold values on the required thickness of the bound layer. The upper graph shows the PCC layer thickness for a jointed plain concrete pavement, and the x-axis is the fatigue cracking threshold value, percent crack slab. So we go from 2% threshold value, excuse me, 2% threshold value for fatigue cracking all the way up to 30%. And you can see that it is a significant impact going from about 10 inches to about 11.5 inches. The reason these bars are constant here is fatigue cracking is not controlling the design. Roughness or faulting may be controlling the design here, so we have a minimum thickness that's required based on this example. This minimum thickness of 10 inches would not be the minimum for all design strategies. This is only an example for a specific condition. This shows again now the same thing, the bottom bar graph, but this is for asphalt fatigue cracking or bottom-up fatigue cracking. So again, y-axis, total asphalt concrete layer thickness, x-axis, fatigue cracking, bottom-up fatigue cracking threshold values, total percent, lane area cracked. And you can see here we go from 2%, which requires about 13 inches of asphalt, down to about 9.5 inches for 30% bottom-up fatigue cracking. Again, the reason these two bars here have a constant 9.5 inches is because other design criteria are controlling, which are basically constant between all the asphalt bottom-up fatigue cracking. So other design criteria are controlling for this specific design example. And again, a minimum 9.5 inches would not be required for all design examples. This depends on the specific examples or site features and other factors within this example. So these two simply show that the distress threshold values are very important or significant for determining the thickness of the bound asphalt layer or bound concrete layer. The same is also true for CRCP. So now let's look at reliability in the same context of a bar chart. This slide shows exactly the same thing as on the previous one, except now we're varying reliability level rather than the distress threshold value. So here you can see for jointed plain concrete pavement, our 50% reliability, we have a cracking, the crosshatch is 15% threshold, and the darker shaded area is 10% fatigue cracking. And this is the minimum thickness through the optimization tool that is the outcome of the Pavement ME software. And again, you can see we're going from 10 inches all the way up to about 10.5 for 15% cracked slabs to about 11 inches for a 10% cracked slab threshold value. The bottom graph is the same, but for based on bottom-up fatigue cracking in an asphalt flexible pavement. So we go from 50% reliability, the crosshatch about 9.5 inches of asphalt for a 15% bottom-up fatigue cracking, and at 50% reliability about 10 inches for bottom-up fatigue cracking threshold value of about 10%, all the way to a 99% reliability where 15% threshold value would be 10.5 inches, and a 10% bottom-up fatigue cracking threshold value at a 99% reliability would require 11.5 inches of asphalt based on the site features, traffic, climate, and other variables used in this example. Again, these two are simply examples to illustrate, demonstrate the impact of reliability on the minimum asphalt layer or minimum concrete layer thickness that's needed. So now let's look at the combined impact of reliability and design criteria, or the distress criteria, on the layer thickness. Again, the total asphalt layer thickness, and this graph versus reliability level for different distress threshold values. The lower being 25% bottom-up fatigue cracks, the black solid line of 15% bottom-up fatigue cracks, the longer dash line of 5% bottom-up fatigue cracks, and the short dotted line or dash line of 2% bottom-up fatigue cracks. And this graph is shown in terms of reliability along the x-axis, going from 75% to 99% at the end here, or the probability of success. So assuming everything is done correctly, we would have, for the 99% reliability, a 99% probability of success of our design exceeding the threshold, not exceeding the threshold value. But you can see that if we're at a 75% reliability level for 25% bottom-up fatigue cracking, that requires 4 inches of asphalt. However, if we require 99% reliability for the 2% limit bottom-up fatigue cracking, we would need 11.5 inches. So again, the slide or this graph displays the significance, importance, or impact of reliability combined with design criteria on our final design, which has to do with construction cost, or the consequences is construction cost, or a lot more. The higher the reliability and the lower the distress threshold value. If we look at this slightly differently, remember the probability of success is 1 minus the probability of failure. So again, that's kind of was defined in Chapter 7 of the Manual of Practice, and this is simply to restate the probability of success is 1 minus the probability of failure. So if we look at this differently now in terms of the probability of failure, basically it's the same reverse of the previous graph. So this is the probability of failure. This is 1% probability of failure going to a 25% reliability of failure for the same distress threshold values and the layer thickness required. So it is a reverse image of the previous slide. Previous slide, probability of success. This slide, plotted as probability of failure. That's basically the only difference. And again, probability of failure is 1 minus the probability of success. So reliability and the design criteria versus construction cost consequence is kind of displayed in this graph. This graph basically illustrates the impact of the design criteria for fatigue cracking on the total asphalt layer thickness required for different reliability levels. Again, just to reinforce the item that both of these values have a big impact on the required layer thickness for all pavement design strategies, not just asphalt, but jointed plain concrete pavement and continuously reinforced concrete pavement. And the agency, in setting these minimum or suggested input values on reliability and design criteria, should consider the consequences and or the construction cost that will be required to build these pavements that are considered acceptable through the Pavement ME design software. So the design criteria and reliability. Individually, the distress threshold value and reliability, considering them individually, not combined, have a moderate to very high impact on surface layer thickness. However, together they have a significant impact on the design. So as reliability increases or as risk decreases, construction costs are going to go up. So the agency, user, designer should make sure we're balancing risk and reliability and construction cost. So now just a simple review summary of reliability and design criteria as inputs to the Pavement ME design software. So our first item was the design criteria should represent the agency's policy for maintaining and operating their roadway system. The second outcome or summary is individually the distress threshold and reliability values have a moderate to high impact on surface layer thickness. Together, they have a very significant impact on design. Remember, selecting a low design criterion or threshold value and a high reliability can result or will result in very costly designs. The other thing to remember that we discussed in Module 3 on reliability and risk, the standard deviation, and also we mentioned this in Module 2 also, the standard deviation of the residual errors for each of the distress types for any pavement design strategy has a significant impact on the reliability and acceptability of the design. So it's important when an agency sets up their calibration or defines the standard deviation of the residual errors. Remember, those get tied back to the hierarchical input level 1, 2, or 3 and how the calibration was done. Also remember, the best available data was used for just about all global, local, or global calibration studies. So the user should ensure that the input values are being derived and determined in accordance with how the design strategies and transfer functions were calibrated. Again, we're kind of building, this workshop is a building of previous modules as we go throughout the workshop. So information we used and presented in Module 2s and 3, and now Module 4.1 will help build on the other modules that we will be presenting. So with that, that concludes our Module 4.1 on design and threshold values. And our next module to be covered will be still on inputs, but we'll go through the climate inputs to the Pavement ME design software.